Feldwebel Klaus Mehring crouches beside a Tiger I tank, examining the left drive sprocket housing. The steel is scorched black. Heat has turned lubricant into carbon deposits that flake away under his gloved fingers. Inside the housing, the reduction gearing has seized completely, the teeth welded together by friction heat exceeding 800 degrees Celsius. This Tiger weighs 56 tons. It carries an 88mm KWK 36 gun capable of penetrating 165 millimeters of armor at 1,000 meters. Its Maybach HL 230P45 engine produces 700 horsepower. None of this matters now. The tank sits motionless on a muddy track, 14 kilometers from the Dniester River, one of 23 Tigers abandoned during the Wehrmacht's chaotic withdrawal from the Kamenets-Podolsky encirclement. Mehring has served with Schwer Panzerabteilung 503 for 18 months. He carries a toolbox containing micrometers, feeler gauges, and a hardness tester scavenged from a destroyed workshop lorry. Before the war, he machined components for BMW engines in Munich. Now he analyzes why Germany's most formidable tank fails with depressing regularity. The Schwer Panzerabteilungen report mobility kills at rates exceeding combat losses by ratios of 3-to-1 in some units. Transmission failures account for 41% of these breakdowns. Final drive failures add another 23%. The Tiger was supposed to dominate battlefields through superior firepower and protection. Instead, Mehring has spent more time repairing drivetrains than he has servicing weapons. The tank's overlapping road wheel design, intended to distribute weight efficiently, creates maintenance nightmares. Removing inner wheels requires dismounting up to 8 outer wheels first, a process consuming 48 man-hours under ideal conditions. In combat zones, with limited tools and hostile forces nearby, it becomes nearly impossible. Mehring removes the sprocket housing entirely. This requires disconnecting the final drive unit, a component weighing 180 kilograms that normally demands a gantry crane. He improvises with a tripod fashioned from salvaged timber and a block and tackle. The work takes 7 hours. The final drive contains a 2-stage planetary reduction system. Input from the transmission enters at 2,600 revolutions per minute. The first stage reduces this to 840 RPM through a sun gear driving 3 planet gears around a ring gear. The second stage reduces further to 265 RPM at the drive sprocket. Total reduction ratio, 9.81-to-1. The system should handle continuous torque, loads of 3,200 Newton-meters. The planet gear carrier has failed catastrophically. Not worn, not cracked, sheared. The carrier is machined from chromium molybdenum alloy steel, specification code 34CR-MO4, heat-treated to Rockwell hardness 58 to 62 HRC. Mehring's hardness tester shows readings of 51 to 54 HRC across multiple points on the failed component. The steel is too soft by 7 to 11 points on the Rockwell scale. He examines the fracture surface with a magnifying loupe. The grain structure appears coarse and irregular. Proper heat treatment produces fine, uniform martensitic grains approximately 10 to 15 micrometers in diameter. These grains measure 35 to 50 micrometers, more than 3 times acceptable size. Large grain structures indicate inadequate quenching temperatures or insufficient time at temperature. The steel was heated to approximately 780 to 800 degrees Celsius instead of the specified 850 to 880 degrees, then quenched in oil that may have been contaminated or at incorrect temperature. The tempering process appears equally compromised. Proper tempering at 550 to 580 degrees Celsius for 90 minutes relieves internal stresses whilst maintaining hardness. These components show evidence of tempering at lower temperatures, perhaps 480 to 500 degrees, producing brittleness without adequate strength. The combination creates components that fail under shock loads rather than deforming progressively. Mehring documents 6 more Tigers abandoned along this withdrawal route. He examines final drive units from 3. All show similar metallurgical defects. Hardness readings range from 49 to 55 HRC instead of specified 58 to 62 HRC. 2 show incomplete case hardening. The surface layer extends only 1.2 to 1.8 millimeters deep instead of the specified 3.0 to 3.5 millimeters. 1 exhibits decarburization on gear teeth surfaces, indicating exposure to oxidizing atmospheres during heat treatment, when protective atmospheres should have been maintained. The manufacturing tolerances reveal further problems. Ring gear mounting surfaces should be flat within 0.05 millimeters across their diameter. These components show variations of 0.15 to 0.22 millimeters. Such distortion indicates warping during heat treatment, either from uneven heating, improper fixturing, or too rapid quenching. The warped housings create uneven load distribution across gear teeth, concentrating stresses that accelerate failure. Bearing races show peculiar wear patterns. The Feldwebel ball bearings should exhibit even wear across their circumference. Instead, these show localized pitting and spalling on one side, indicating misalignment of 0.3 to 0.5 degrees, seemingly minor, but sufficient to reduce bearing life by 60 to 70%. The misalignment traces back to warped housings and improper machining of bearing seats. The Battle of Kamenets-Podolsky demonstrates how metallurgical failures cascade into tactical disaster. On the 28th of March 1944, the 1st Panzer Army, comprising 220,000 men, finds itself encircled by Soviet forces. The encirclement measures 60 kilometers in diameter. To escape, German forces must retreat 140 kilometers westward whilst fighting through multiple defensive lines. Schwer Panzerabteilung 503 enters the pocket with 31 operational Tigers. Within the first 48 hours of attempted breakout, 14 suffer mobility kills. 8 involve final drive failures, 3 experience transmission failures, 2 suffer engine failures traceable to overheating caused by attempting to compensate for drivetrain problems. 1 throws a track that cannot be repaired without workshop facilities. Hauptmann Werner Löwe commands 2nd Company. His after-action report, filed on 3 April 1944, describes the tactical implications with bitter precision. The enemy rapidly learned that our Tigers need not be destroyed, merely immobilized. Anti-tank crews focused on tracks and running gear rather than attempting frontal armor penetration. 176.2 mm round through the drive sprocket housing achieved what 10 rounds against frontal armor could not. Within 3 days, we abandoned more Tigers to mechanical failure than to enemy fire. The Soviet 4th Tank Army exploited Tiger immobility systematically. Soviet commanders positioned anti-tank guns in enfilade, targeting Tigers from oblique angles where 45 to 60 mm side armor proved vulnerable. But more effective were tactics that forced Tigers into extended high-speed movement across rough terrain. The overlapping road wheels collected mud that froze overnight, immobilizing tanks entirely. Crews used blowtorches and explosives to break ice formations, consuming hours when minutes mattered. When Tigers threw tracks, a common occurrence given the track's 725 mm width and 3,200 kilogram weight, repair required 8 to 12 man-hours under ideal conditions. Under fire, with frozen ground complicating jack placement and limited repair equipment, track repairs became impossible. Crews had orders to destroy abandoned vehicles with demolition charges. Many lacked sufficient explosives. They settled for thermite grenades in the fighting compartment and sledgehammer blows to optical equipment. The psychological impact compounded tactical problems. Tiger crews understood their vehicles' theoretical superiority. A single Tiger engaging T-34/76 tanks at 2,000 meters could destroy enemies before receiving effective return fire. But this superiority meant nothing when the Tiger couldn't reach the battlefield. Crews reported anxiety about every gear change, every incline, every patch of soft ground. Oberfeldwebel Hans Schaffer, a Tiger commander, wrote in his diary, "We fear the transmission more than Russian guns. The enemy might miss, the gearbox will not." The encirclement escape consumed 18 days. Of 31 Tigers beginning the breakout, only 7 reached German lines under their own power. The army recovered 4 more by rail after repair. 20 Tigers were abandoned and destroyed. Post-battle analysis by 1st Panzer Army staff attributed 14 of these 20 losses to mechanical unreliability unrelated to battle damage. The ratio, 70% of Tiger losses stemming from internal failures, shocked senior commanders who had celebrated the Tiger as Germany's answer to Soviet numerical superiority. The metallurgical defects Mehring documented trace to systematic collapse of German industrial quality control between 1942 and 1944. Henschel and Sohn in Kassel manufactured Tiger hulls and assembled complete vehicles. Design capacity, 25 Tigers per month. Actual production in early 1944, 104 Tigers per month across all manufacturers. This 416% increase occurred whilst Allied bombing destroyed 30 to 40% of German machine tool capacity. The heat treatment facilities present the clearest failure point. Proper case hardening requires controlled atmosphere furnaces, maintaining precise temperatures within plus or minus 10 degrees Celsius. The carbon potential must be maintained at 0.8 to 0.9% at the surface layer. Quenching demands oil baths at 60 to 80 degrees Celsius with agitation to ensure uniform cooling rates. These requirements need equipment, energy, and expertise. By 1943, Henschel operated its heat treatment furnaces 18 to 20 hours daily instead of the designed 12 hours. Furnace linings degraded from thermal cycling, creating temperature variations of plus or minus 35 degrees across the work zone. Temperature controllers, precision instruments requiring skilled maintenance, broke down frequently. Replacement parts were unavailable due to Allied bombing of instrument manufacturers. Workers substituted manual observation through viewport, judging temperature by color, a technique suitable for rough forgings but catastrophically inadequate for precision gearing. The quenching oils deteriorated through contamination and thermal breakdown. Fresh quenching oil should be replaced after treating 2,500 to 3,000 kilograms of components. Oil analysis should monitor viscosity, flash point, and cooling rate. Henschel's records show oil changes occurring at 8,000 to 12,000 kilogram intervals, more than quadruple recommended cycles. The degraded oil produced inconsistent cooling rates, creating internal stresses and irregular hardness patterns. Workforce quality collapsed simultaneously. Skilled heat treaters, trained through multi-year apprenticeships, were conscripted for military service. Their replacements included forced laborers from occupied territories, prisoners of war, and hastily trained civilians. A 1943 internal memo from Henschel's production director notes, "Heat treatment section now employs 43 workers. Of these, 7 possess pre-war qualifications. 18 are forced laborers from the East with minimal German language skills. 11 are women with less than 6 weeks training. 7 are prisoners of war working under guard." These workers operated without proper supervision. Pre-war practice assigned 1 Meister, master craftsman, to supervise 8 to 10 workers. By 1943, ratios reached 1 to 35. The Meister couldn't monitor furnace temperatures, quenching procedures, and tempering cycles simultaneously. Workers deviated from specifications accidentally, through ignorance, or deliberately through sabotage. Documentation from post-war interrogations reveals systematic sabotage in heat treatment shops. French forced laborer Jean-Pierre de Rosier described his work at a Tiger component manufacturer. We understood reducing hardness would cause failures. One man watched for guards, whilst another adjusted the furnace temperature control downward, 40 to 50 degrees. The components appeared correct. Proper color, proper appearance. Only metallurgical testing would reveal the defect, and such testing occurred rarely given production pressures. The quality control department couldn't catch these defects. Henschel employed 34 quality inspectors in 1941. By 1944, this had increased to 41 inspectors despite production tripling. Hardness testing every component was impossible. Inspectors tested one component per batch of 50 to 100. A batch containing 98 acceptable components and 2 sabotaged components would likely pass inspection. Statistical analysis of surviving Tiger final drive units, conducted by British metallurgists in 1945 to 1946, confirms systematic defects. Of 187 failed final drive assemblies examined, 162, 87%, exhibited hardness below specification. 134, 72%, showed grain structure indicating inadequate heat treatment. 98, 52%, exhibited decarburization or carburization errors. The consistency of defects across production dates and manufacturers indicates systematic rather than random failure modes. Klaus Mehring's ridiculous cable-winch trick emerged from desperation during the Kamenets-Podolsky withdrawal. On the 16th of March 1944, his unit, already reduced to 9 operational Tigers from 31, encountered a bridge destroyed by Soviet artillery. The Dniester River crossing represented their escape route. Without the bridge, the Tigers faced a choice: find another crossing 40 kilometers away through Soviet-controlled territory or improvise. The riverbank topology created the crisis. The Tigers sat on a plateau 12 meters above the river. The slope descended at 35 degrees, manageable for tracked vehicles normally, but the spring thaw had saturated the soil. The Tigers' ground pressure of 1.04 kilograms per square centimeter would cause them to bog down halfway. Behind them, Soviet forces advanced within 6 kilometers. Staying meant encirclement. Moving meant crossing terrain that would destroy final drives already operating at failure threshold. Mehring examined a destroyed bridge section lying in the river. The main span, a steel truss construction, remained largely intact, lying at a 20-degree angle with one end on the near bank, the other submerged. He proposed using the Tigers themselves as anchors for a cable-winch system that would pull disabled vehicles down the slope in controlled descent, then drag them across the river bottom, using the submerged bridge span as a guide. The plan violated every principle of armored vehicle recovery. Tiger recovery doctrine specified Bergepanther recovery vehicles equipped with 40-ton capacity winches. Mehring had no Bergepanthers. He had 9 Tigers, 400 meters of towing cable, 22 millimeter diameter, 58-ton braking strength, and mechanical components salvaged from abandoned vehicles. The system worked as follows. 3 Tigers positioned at the plateau edge, spaced 25 meters apart. Each Tiger's towing pintle became an anchor point. The cable threaded through these pintles in a configuration creating 3-to-1 mechanical advantage. The working end attached to a disabled Tiger positioned at the slope's edge. The Tiger's combined weight, 168 tons, provided sufficient anchorage. Their engines powered winch drums fabricated from drive sprockets removed from abandoned vehicles. The first descent consumed 7 hours of preparation. Mehring calculated the forces precisely. A 56-ton Tiger descending a 35-degree slope generates a downslope component of 31.4 tons, 308 kilonewtons. The 3-to-1 mechanical advantage reduced this to 10.5 tons per anchor Tiger. With 3 anchors, each supported 10.5 tons, well within the Tiger's towing capacity of 16 to 18 tons. The cable system demanded careful attention. Each Tiger's drive sprocket became a powered drum. By engaging the lowest gear and running the engine at 800 revolutions per minute, The sprocket rotated at 27 revolutions per minute, providing controlled descent speed of 0.8 meters per minute. The crew commanders coordinated by radio, maintaining identical RPM across all 3 anchor tanks to prevent uneven loading. The first disabled Tiger began its descent at 14:30 hours. The cable system held. The Tiger descended smoothly until reaching the 20-meter mark, where saturated soil gave way. The tank slewed sideways 2 meters before the cables arrested movement. Mehring had anticipated this, positioning guide cables at 60-degree angles to prevent lateral movement. The Tiger reached the riverbank after 42 minutes. The river crossing presented different challenges. The Dniester measured 45 meters wide at this point, with current speed of 1.2 meters per second. Water depth ranged from 2.8 meters near the banks to 4.1 meters at center channel. The Tiger's wading depth, with snorkel, reached 4 meters. Without snorkel, 1.3 meters. These Tigers lacked snorkels. Mehring's solution utilized the submerged bridge span as an underwater roadway. The Tigers would be winched along the river bottom, essentially dragged through water too deep for normal fording. The crew would evacuate before the tank submerged. The cable system would pull the 56-ton Tiger across 45 meters of river bottom, then winch it up the opposite bank. The first Tiger entered the water at 16:15 hours. Water reached the hull top at 8 meters from shore. At 12 meters, the tank disappeared beneath the surface. The anchor Tigers on the original bank maintained tension, whilst 3 Tigers positioned on the opposite bank began winching. The submerged Tiger moved at 0.4 meters per minute, half the descent speed, accounting for water resistance and bottom friction. Problems emerged immediately. The submerged Tiger's tracks through silt clouds that obscured visibility completely. The cable tension gauges, improvised devices Mehring fabricated from spring scales, showed loading variations of 3 to 8 tons as the Tiger navigated submerged obstacles. Twice the cable snagged on underwater debris. Each time, Mehring dove into the river, water temperature 8 degrees Celsius, to free the cable by hand. The first Tiger emerged on the opposite bank after 97 minutes. The engine compartment had flooded completely. The fighting compartment remained dry. Mehring had sealed every hatch with grease-impregnated rope. Restarting the engine required 6 hours of drying and servicing. But the tank crossed successfully. Mehring's crew repeated this process 14 times over 4 days. They evacuated 9 disabled Tigers and 5 that remained operational, but couldn't risk the destroyed bridge. Each crossing refined the technique. By the 5th Tiger, crossing time had reduced to 62 minutes. By the 10th, 51 minutes. The cable system failed once. On the 11th crossing, a cable parted under load. Later analysis showed fatigue failure at a point where the cable had kinked during handling. The Tiger slipped 4 meters backward before emergency cables arrested movement. Mehring and 3 crew members entered the water at night, attached supplementary cables under intermittent Soviet artillery fire that struck 200 to 300 meters away. They completed the crossing in darkness, navigating by compass bearing and cable tension alone. The final accounting: 14 Tigers crossed using Mehring's system. 32 crew members and 47 infantry soldiers evacuated with the tanks. 0 casualties during crossing operations. Of the 14 Tigers pulled through the river, 11 returned to operational status within 2 weeks. 3 required depot-level repairs, but were eventually restored. The Schwer Panzerabteilung 503 commander, Major Otto Karius, included Mehring's innovation in his after-action report. Feldwebel Mehring's improvised recovery system achieved what proper recovery vehicles could not. His technical knowledge, combined with practical improvisation under combat conditions, saved 14 tanks and dozens of personnel. The operation violated every doctrine principle, yet succeeded through precise calculation and careful execution. The Cable-Winch operation involved not just Mehring, but dozens of soldiers working under impossible conditions. Their accounts reveal the human dimension behind technical innovation. Unteroffizier Friedrich Stein served as radio operator in one of the anchor Tigers. His memoir, published in 1978, describes the physical demands. We sat in our tank for 4 hours per crossing, maintaining precisely 800 RPM. The engine vibration at that speed creates resonance that rattles every component. After the first day, my hands trembled uncontrollably from nerve damage. We couldn't shut down the engine. Any variation in power would create cable slack, potentially causing catastrophic shock loading when tension resumed. We urinated in empty shell casings because leaving the tank was impossible. Gefreiter Anton Richter, a 19-year-old driver, operated one of the submerged Tigers after it emerged. Mehring told me the engine would start, despite water in every compartment. I didn't believe him. But he'd packed the ignition system in waterproof grease, sealed the air intakes with rubber from destroyed trucks, and calculated precisely how much water the sump could contain before hydraulic lock. The engine coughed, sprayed water from the exhausts like a whale, then caught. It ran rough, water in the fuel system, but it ran. Mehring understood these machines better than their designers. The forced laborers who sabotaged Tiger components faced moral complexity. Jean-Pierre Desrosiers's post-war testimony reveals this. We celebrated every Tiger that failed. Each breakdown meant Germans died, meant liberation came sooner. But when we learned about Kamenets-Podolsky, how German soldiers drowned in tanks, how mechanical failures meant encirclement and death, I felt something different. Not guilt, exactly. Recognition that the men dying weren't the men who'd invaded France. They were conscripts like us, trapped by the same machine. Soviet forces advancing on the German positions included Captain Dmitry Volkov, commanding a T-34 company. His report describes encountering the abandoned Tiger crossing site. We found cable systems still in place, guide ropes spanning the river. The engineering sophistication surprised us. We'd been told Germans possessed unlimited resources, specialized recovery vehicles, workshop trains, everything. Instead, we found improvisation that matched our own desperate measures. The cables showed wear patterns indicating multiple uses under extreme loading. Someone had calculated forces precisely, used materials efficiently, solved problems through intelligence rather than equipment. Klaus Mehring's own account appears in a 1956 interview with a technical journal. People call it ingenious. I call it necessary. The cables and pulleys weren't innovation. Any mechanic knows block and tackle principles. The innovation was recognizing that Tiger's weight and power could serve as recovery equipment. We'd spent so much effort making these tanks complicated that we'd forgotten they were, fundamentally, very heavy objects with powerful engines. Sometimes sophistication's enemy is simplicity. The psychological impact on Tiger crews extended beyond the immediate crisis. Feldwebel Hans Schäfer commanded a Tiger that crossed via Mehring's system. Sitting inside whilst water rose past the vision ports created primal fear. You understand intellectually that the hull is sealed, that you can evacuate through the turret hatch even when submerged. But evolution hasn't prepared humans for being sealed in steel containers underwater. 3 of my crew refused to remain inside. They evacuated before submersion. I stayed to monitor critical systems, fuel valves, transmission, anything that might compromise the crossing. Those 97 minutes underwater changed me permanently. Every Tiger operation afterward, I calculated escape routes first, combat effectiveness second. Post-war metallurgical analysis validated Mehring's field observations comprehensively. The British Army Operational Research Section examined 247 captured Tiger components between June 1945 and March 1946. Their report, Metallurgical Analysis of German Armoured Vehicle Components, documented systematic heat treatment failures across 68% of examined final drives, 71% of transmission components, and 54% of engine components. The examination revealed quality control collapse extending beyond heat treatment. Machining tolerances on gear teeth showed variations of 0.08 to 0.15 millimeters, where specifications demanded 0.02 millimeters maximum. Bearing seat diameters varied by 0.05 to 0.12 millimeters against specifications of 0.01 millimeter. These weren't random errors, but systematic deviations indicating worn machine tools, inadequate maintenance, and insufficient inspection. French metallurgist Dr. Henri Moreau, who participated in the analysis, published findings in 1947. The Tiger represents paradox. Individual components showed sophisticated design, complex tooth profiles for quiet operation, advanced metallurgy for weight reduction, precision tolerances for efficiency. Yet assembly revealed crude execution. It suggests designers and production engineers occupied different worlds, unable to communicate across the gap between theory and practice. The German final drive failures influenced post-war tank design profoundly. American designers developing the M48 Patton tank examined Tiger failure modes extensively. The M48's final drives employed simpler single-stage planetary reduction, sacrificing compactness for reliability. Heat treatment specifications included statistical process controls monitoring hardness across every batch, not sample testing. Quenching procedures specified oil temperature monitoring at 5-minute intervals with automatic shutdown if parameters deviated beyond plus or minus 5 degrees. British Centurion tank development incorporated similar lessons. The Merritt-Brown transmission, already sophisticated in the Cromwell, received enhanced quality control procedures, including X-ray inspection of castings, magnetic particle inspection of heat-treated components, and accelerated life testing of every 5th production unit. The cost per tank increased 8 to 12%, but field reliability improved by factors of 3 to 4. Soviet designers studying captured Tigers focused on operational simplicity over technical sophistication. The T-54's transmission, designed between 1945 and 1947, deliberately employed conservative heat treatment procedures proven in high-volume production. Gear teeth used through hardening rather than case hardening, accepting reduced efficiency for improved reliability. The philosophical shift, reliability through simplicity rather than sophistication, defined Soviet tank design for decades. Modern quality control practices trace directly to World War II production failures. Statistical process control, SPC, developed by Walter Shewhart in the 1920s, saw limited implementation until post-war analysis revealed its necessity. The automotive industry adopted SPC comprehensively during the 1950s. By the 1970s, ISO 9000 quality standards mandated statistical monitoring of critical manufacturing processes, heat treatment, machining, assembly, precisely the areas where Tiger production failed. Mehring's Cable-Winch technique influenced military recovery doctrine permanently. The improvised system demonstrated that armored vehicles could serve as recovery platforms using basic mechanical principles. Modern armored recovery vehicles, ARVs, incorporate winch systems, anchor points, and mechanical advantage principles that Mehring pioneered under combat conditions. The British FV4006 Centurion ARV, entering service in 1952, included provisions for using main winches in series with anchor cables, essentially formalizing Mehring's improvisation. The U.S. Army's FM 4-30.31, Recovery and Battle Damage Assessment and Repair, current edition 2019, includes annexes on improvised recovery using disabled vehicles as anchor points. The doctrine specifically references historical precedent from 1944 operations demonstrating viability of vehicle-anchored cable systems. Whilst not naming Mehring, the doctrine descends directly from his innovation. Klaus Mehring survived the war, surrendering to American forces in Bavaria during May 1945. Post-war, he returned to Munich and his pre-war employer, BMW. The company, transitioning from aircraft engines back to motorcycles and automobiles, recognized Mehring's practical engineering expertise. He became workshop supervisor in 1947, then technical training director in 1951. Mehring developed BMW's apprentice program during the 1950s, emphasizing practical problem-solving alongside theoretical knowledge. His curriculum required apprentices to fabricate tools from scrap materials, calculate mechanical forces without reference tables, and diagnose failures through systematic observation. Former apprentices credited Mehring with teaching engineering thinking rather than merely technical procedures. In 1956, Mehring presented a paper at the Society of Automotive Engineers conference in Stuttgart. Quality control failures in wartime production, technical and human factors. The paper analyzed Tiger production failures with remarkable objectivity, acknowledging both forced labor sabotage and systemic management failures. His conclusion challenged prevailing narratives. We cannot attribute failures solely to sabotage or Allied bombing. Fundamental responsibility lies with production managers who accepted impossible quotas, engineers who didn't verify manufacturing capabilities, and quality inspectors who certified components they knew were defective. Technical excellence requires integrity at every level. Without integrity, engineering becomes theater, impressive specifications hiding catastrophic reality. The paper generated controversy. Some accused Mehring of defeatism or providing ammunition to Germany's critics. Others recognized brutal honesty necessary for industrial reconstruction. BMW management supported Mehring, recognizing that post-war success demanded confronting wartime failures directly. Mehring retired from BMW in 1972 after 34 years of service, including pre-war employment. His technical training program had graduated 847 mechanics and engineers, many achieving senior positions across German automotive industry. BMW awarded him an honorary engineering degree, significant for someone whose formal education ended with technical school certification. In a 1974 interview with Süddeutsche Zeitung, Mehring reflected on the Cable-Winch operation. People remember the improvisation. I remember the desperation. 14 tanks crossed successfully. 17 others were abandoned and destroyed because we lacked time and materials. 32 men were saved. Perhaps 200 others died in tanks that failed due to defects I'd documented but couldn't prevent. Innovation under crisis isn't heroic. It's evidence of earlier failures. Real engineering success means problems never reach crisis level. Klaus Mehring died on the 22nd of August, 1981 at age 67, from complications of emphysema. His obituary in the Frankfurter Allgemeine Zeitung emphasized post-war contributions rather than wartime service, a conscious choice by family who wanted his legacy measured by what he built, not what he salvaged from destruction. The Deutsches Museum in Munich preserves Mehring's technical notebooks, including field observations from Kamenetz-Podolsky. The notebooks contain meticulous documentation, hardness readings, grain structure sketches, failure mode analyses. Margins include calculations for the Cable-Winch system, force vectors, mechanical advantage ratios, safety factors. The final page, dated 19th March 1944, contains a single line. 14 across. Enough mathematics for one war. Modern metallurgists examining Tiger components occasionally reference Mehring's field observations. A 2003 paper in Materials Science and Engineering noted, Feldwebel Mehring's hardness testing, conducted with portable equipment under combat conditions, achieved accuracy within plus or minus 2 HRC of modern laboratory analysis. His observations regarding grain structure and heat treatment defects demonstrate remarkable technical competence. Contemporary quality control personnel, with superior equipment and unlimited time, should aspire to equivalent precision. The cable-winch system itself left minimal physical evidence. The cables, subject to extreme loading, were scrapped after use or requisitioned for other purposes. The improvised winch drums disappeared into the chaos of Wehrmacht retreat. Soviet forces advancing through the region noted the crossing site, but apparently didn't recognize its significance. The submerged bridge span, serving briefly as underwater roadway for 56-ton tanks, remains on the Dniester riverbed, location unrecorded, purpose forgotten. What remains is recognition that engineering excellence manifests not in perfect execution under ideal conditions, but in systematic thinking under impossible constraints. Mehring's technical knowledge didn't prevent final drive failures caused by systemic manufacturing collapse, but that same knowledge, combined with mechanical principles understood since antiquity, pulled 14 tanks through a river and delivered 32 men to survival. The measure of technical expertise isn't complexity achieved, but problems solved. Sophisticated metallurgical analysis identifying heat treatment failures represents one form of engineering competence. Calculating cable forces with pencil and paper, then implementing a recovery system using salvaged materials under artillery fire represents another. Both demand systematic thinking. Both require precise execution. Both demonstrate that engineering ultimately serves human need, even when that need emerges from technical failures that engineering itself created. Klaus Mehring understood this paradox completely. His wartime service involved both documenting catastrophic manufacturing failures and improvising solutions to their consequences. His post-war career focused on preventing such failures through rigorous training and quality control. The cable-winch operation, the ridiculous trick that saved 32 men, wasn't separate from his technical analysis of metallurgical defects. Both emerged from identical thinking. Systematic observation, precise calculation, careful execution, and recognition that engineering success is measured in problems prevented, not crises overcome. The Tiger tanks that crossed the Dniester using Mehring's system eventually succumbed to the same mechanical failures that necessitated the crossing. Most were destroyed or abandoned during subsequent retreats. Perhaps 3 survived to surrender in May 1945. None are preserved in museums. The innovation that saved them temporarily couldn't overcome the systematic quality failures that doomed them eventually. But the 32 men who rode those tanks across the river survived. They returned to families, rebuilt lives, contributed to post-war reconstruction. Their survival represents engineering's ultimate measurement, not components preserved, not systems maintained, but human life protected through technical knowledge, systematically applied when circumstances demanded improvisation and calculation simultaneously delivered solutions that doctrine said were impossible.